is biology. So biology is biology-driven sort of activity. We're using computer tools to do biology, the same way chemists use chemistry to understand biology. Right? And so there's a concept of big data also, so that's evolving. What I'm talking about today will be different next year, but at the top there is that fourth wave that we get small brain hard drive, things are playing. Starts playing from 1956. And of course here is the 5 terabyte drive that is 6 times my laptop. And that's from last year. You can get even bigger ones now, or smaller ones for the same or more data. I mean this is not, I'd say 15, 16 years ago, I purchased a 1 terabyte hard drive for a data center at the cost of $250,000. 14 years ago. So it's things have evolved. Things have evolved. And they will continue to evolve. So this is a related slide that Mark had over here today. It is the whole idea of opportunity and the size of data sets and the use of data from one data center to another data center. One of the reasons why it's going to become impractical to do so is that it's going to take years now to move large data sets. And 5 petabytes is about the scale. It's a bit smaller than that, but it's the order of magnitude that the ICGC data set is in right now. So this is a 1 to 1 in 5 petabytes. And so that kind of data size set is not going to be movable into the data center anymore. And if you want to have access to the whole data set, if you want to be comprehensive, if you need the whole data set for the kind of questions you want to ask, then it's going to be impossible to one host and two to get, because they're planning these. The folks at Amazon, if you actually talk to them about moving large data sets like that, they tell them it's much less than just ship the hard drives. And it's like moving shipping stuff. And so if you have this in one place and you want to move to another place, you want to physically move the data on an airplane, which is just not use the internet, or to actually, and what has become the solution now is to actually move your software to where the data is and do the computes there. And that's what we're going to do this week. And we're going to do it in a couple of environments. So the first part of the week, we're going to do that in Amazon, so commercial cloud, public commercial cloud provider, Amazon Web Services. And in the second half of the week, we're going to do it at the Laboratory, Cancer Genome Laboratory, which is a resource at the University of Toronto that has been set up by folks at the OICR. And so it's going to be, you'll see a very different access, somewhat different access, somewhat different. What's going to be the difference, though, is which data set is where, and which data set is spent on Amazon versus on the collaboratory, and which tools are easily interoperable and pipelines and so forth. And so you'll be playing with that this week, and you'll have a chance to study that, to see the differences. So what I just said, data sets are in the petabyte scale, if not exabyte, pretty soon, and data and security rules, things that Mark talked about, will be somewhere and not in your own hands. So basically, it's a lot easier to apply standard sort of rules for accessing the data around where the data is, as opposed to supporting those rules around your laptop. And you should not have any of this data on your laptop anyway, because it's stealable and not physically secure and so forth. And so not necessarily the data we're going to study this week. So this week we're going to talk about controlled access data, but the actual data you're going to be using is going to be open data, because we didn't get you permissions to have access to controlled access data. But you'll see how to do that in the lecture today. So we talk about openness, there's all sorts of different things. So there's open access, which usually refers to publications. There's open source, which usually refers to source code. Open data, which refers to data. And open courseware, which refers to the material that we teach with here at this workshop. And so we talked about, so the bioinformatics agent is databases. And the way this information is organized is sort of a key thing to understand what is usable for a given database. And it sounds a little crazy, but you should put something in a database, you should be able to go back out. I've had experiences with large-scale projects where we put things in databases and then we can't find it anymore. And it all has to do with identifiers and the fields and the metadata where things are at, and if that's not kept track properly and the wrong identifier is in the wrong field, then you use a query engine, which just looks for that metadata in a certain field that doesn't look in the other field, and it doesn't find it. And this has happened in large organizations, which will remain nameless because it's too embarrassing, but it's some of the big players that are on this planet in the bioinformatics field. Maybe you should give me a beer, I'll tell you. No, you don't buy me a beer, but if I have a beer. So obviously, once a database is well organized and well structured, and it sort of standardizes ways you can talk to it, then you can write tools that will do that. So it's not just you doing head queries through a web interface. You can do an API. So API is an application programming interface, allows you to talk from software to talk to your database and generate your own interface, your own website, your own data sets, and so forth. So having that available is a really sort of key thing to having a good database. And the really sort of key thing on organizing a database is what your data model. And so here's an example of data model would be that whenever I change the DNA sequence in my DNA sequence database, I will modify the unique identifier for that sequence, because the unique identifier for that sequence is just X, Y, Z, to say those 3 letters. And I change one nucleotide, and now to know that the system has changed, my data model says I will change the identifier for that, because it's not the same sequence anymore, and therefore it has a new identifier. And so databases like EMBL and GenBank have done that now. They both like that at the beginning, but now they have identifiers that change whenever the sequence changes. And so that's what the data model is. So whenever you change a sequence, are you going to change the date stamp on it? Yes, we're going to do that. If you change a feature, don't change the sequence. You change the date stamp or the unique identifier for the sequence. All these rules that you put around a database, it's important to sort of define up front before, and you publish those ideally, or at least put them on your website to explain to the people what these various fields mean, what is the purpose of this database, what's being maintained, how frequently is it getting updated, and all of these things. So those are key things in thinking about a database. And so just a few images to sort of explain some of the things we think about. So the metadata, which is basically data about data, right, is you have things like create dates, update dates, submitted ORCID. Does anybody know what ORCID is?
Yeah, it's like my researcher for researcher.
Yeah, so it's each of us, we all have an ORCID ID. If you don't know your ORCID ID, you should know your ORCID ID. If you don't know, you can go to the ORCID website and they can tell you what your ORCID ID is, or you can register and have an ORCID ID. And that soon all journals will require that anyway. So when you submit a paper, many of the journals, definitely the PLOS family does that, and the BMC, probably many of the open access journals. And ideally, this will percolate to things like PubMed and so forth. So you'll be able to query by ORCID ID for a given investigator. So it'll be a lot better because there's some names you can imagine happen very frequently in the databases, but represent different people. They just happen to have the same last name in the first initial. And so this will protect for that, against that. So the publisher looked at it and so forth. So the data would be a DNA sequence file. That would be an example of data. A cosmic record. Does anybody know what cosmic is? So it's a somatic variant database. I'm going to talk about it a bit later. Protein-protein interaction data. So you know what that is. We don't talk about it in this course, but so interaction database. Intact is sort of the biggest one probably at the EBI, and that's a database where you say protein A interacts with protein B. It's usually protein, but protein DNA, protein RNA, protein small molecules, and so it's this entity interacts with that entity, and so the record is A binds to B. You may have more metadata saying which part of A binds with which part of B, or A binds to B only when B is phosphorylated, and so there's all sorts of metadata you can put around that. But the protein-protein interaction database is an example of a record. Titles of the book or books themselves. So a storage system could be a box on your shelf. That's a storage system. Oracle, MySQL, sort of commercial and open access relational database systems. Binary files could be a place where you just a file system. Text files and bookshelves. So a query system could be a list you look at. So I'm saying you have a list of all the things that are on your bookshelf, and you say, I'm looking for this book, or where is it on my list? And so you can just look down the list, and that's a sort of query system. Catalog is a query system. Index file is a query system. SQL, structured query language, is a query system. Elasticsearch, which are now used in cloud computing, systems that allow to look at big data, is another query system. And grep, which is a Unix tool, which you all practiced last week, right? grep, yes. Okay, good. I'll test you on that. No, you forgot. You already forgot grep. Grep is a good one. Anyways, we'll come back to grep later. And then the information system. So the information system is like the whole enchilada. So you could, Google is like an information system, right? The Library of Congress is a library system. There's an information system. Altig at NCBI is an information ensemble at DBI. UCSC Genome Browser is actually multiple browsers, multiple organisms. It's a whole sort of information system with the parts talking to each other. And ICGC is also a big information system that we'll talk a bit about today. But so all the information system is sort of the big envelope, the ship that your label that has a reference often that you can refer to. But under there are many layers of things that are sort of key to understand as well. So the NCBI itself allows you the system to submit data, to download data, to learn. It has a whole teaching section. It has a whole development and tool section. It has lots of analysis tools and research and just places where you talk. The NCBI itself is a core group of people that do research, and so the research is available too. So we talked about the DNA sequences and how they're shared and so forth. So actually, the nucleotide sequence are part of this international nucleotide sequence shared system where three centers, so the Europeans, the Americans, and the Japanese, share the data, the content of their respective databases. There are 3 points of entry into one database. So your sequence is submitted either through Europe or Japan or the US, Bethesda, NIH, and NCBI. Ends up into a GenBank DNA, European Nucleotide Archive, or DBJ DNA database of Japan, into one repository. And they each issue accession numbers for records that were submitted to them. But let's say a GenBank accession number will be in the ENA database and will be queryable with the same accession number. So it doesn't get a European accession number because it got one already from the US. And so these 3 databases sort of sync up every night. And so they're actually, within a day, they're the same database of each other. And so there's a really sort of good example of sharing the load of submission, updates, and maintenance of the archive and the whole repository across 3 different countries. It's sort of, and the other sort of benefit there is there, which was not thought about I think at the time, was actually you have a help desk in 3 different time zones. And so you have, whenever you're awake, you can sort of call somebody to help you. And hopefully, if you're only awake in the middle of the night and you're in North America, you speak some good Japanese, and you can call the Japanese people. But, I mean, they all have email, and so, you know, but there are basically this help around the world for this resource. And CBI, of course, has many other things besides sequence data. And so this, if you go to this query page, you can actually, and you put in the query all filters and square bracket, it gives you the number of records in each resource. And so it gives you an idea of how big. If you look at previous lectures, I have this slide every year, so I update it every year. So you can go see how much the database is going to do that exercise, see how the resources have grown over the years. And so NCBI offers PubMed, PMC, DBGAP, and ClinVar for health data, WGS and RefSeq, example of genomic data, the sequences and 3D structures of proteins world, the NF, and the chemical world, they have PubChem and biosystems. So it's just a very sort of quick overview of the types of things people do. And now I'm going to switch a little bit and talk about file formats. And so I'm going to talk about DNA sequences, and I'm today, but it's and BCF, I think also new others doing new BCF files. So you'll have that throughout the week and all the various file formats that you have to work with. Right now, there's actually on the UCSC website, there's the UCSC journals, there's actually a really good sort of table which has definitions of all the various file formats, or many of them that are used in the DNA world and RNA and DNA type world. And I invite you to go look at that if you're interested in that. So databases are now, I've sort of split them, I've sort of done that for a few years now, so I've split them into two sort of classes, two categories. One is like a primary or archival, and the other one is secondary or curated, although some sort of fit in both sides. And so GenBank is not really curated, although there is some curation that goes on, and curation being sort of like we talked about, sort of the handwork that has to be done on records. It's hard to automate and so forth. And so archival tool, which is like GenBank, Unicode, it's a protein resource, which is all the abstracts, PubMed Central, which is all the open access journal abstracts, Intact is a protein interaction database, ICGC, the data for that, ETA is sort of it's the equivalent of dbGaP on the European side. And so the secondary database is also curation, which takes place RefSeq. So RefSeq is actually from NCBI was invented RefSeq was a way to take, so the issue with the GenBank records is that they're archival and they belong to the user or the submitter that submitted that record. And then NCBI wanted to have a system where they wanted to update those records. But what they did is they're part of an open access database. So what they did is they took the best, and also from gene and bacteria, for which there's probably been sequenced 10,000 times. So there's 10,000 entries of beta-gal in GenBank. But what we at the time wanted to do with RefSeq is to have one copy of everything. So we want to have one copy of the E. coli genome, all the genes there, one copy of the human genome, and all the genes there, and every other analysis and so forth. And so RefSeq is a reference sequence of each organism in a database. So how does NCBI get that data? Well, basically they go through the existing compendium and they take the best what they think is the best one, and they annotate it in the best possible way. So they curate it so that, and they curate it in a standard way across all organisms and all across, so that it will be annotated the same way. And so RefSeq is really, so if you talk about the mRNAs, RefSeq sequences that are currently in GenBank, or not GenBank, at the NCBI, is a copy of every mRNA for which there's a copy. So it exists in real life, and there's a copy, but it references an existing record that was done by some other group. And so they've taken it from other groups and built a uniformly annotated data set from existing stuff that's in GenBank. So RefSeq sort of genes is sort of similarly, it's the curation of all the genes, concepts, curation of all the different organisms themselves. Unicode, Chromium, because I'm not done in hands, and so it's going to be it's basically the phenotype data associated with all the human genes, and so it's sort of disease, genetic disease associated with all the various genes and so forth. The MODS, the model organism database, is an ICGC. So why are the MODS so important? So the model organisms databases are so important because that's where all the experiments have been done on mouse, on zebrafish, C. elegans, yeast, and so forth. And so there's a lot of inferences, understanding of what genes do, function, that has been done on the model organisms, and then there's homology between the model organism genes and the human genes, and so then you projection of not only directly, sometimes needs to be validated some other way, but there's often, you can sort of speculate on what the function of that gene is in humans when you know what it does in other organisms. And so that's how it's basically the function determined through the MODS helps us understand what it does in humans. And then NAR, Nucleic Acid Database, Nucleic Acid Research Journal, has a yearly database issue that used to every year would sort of publish the top 100 or the top 20 databases that they publish every year. And it would be the same ones, and then so a few new ones would get added over time. But what's happened is that issue got so big, they had to split it to two. So there's a few articles which are repeated every year, but most of them are new ones for that year. So any database that's sort of in the in-group gets published every second year. And so if you want to look at all the databases, the top databases in the world, you have to look at 2 issues worth of NAR this year and last year's. And so in January, every year, there's a new issue. So NCBI, EBI, and DBJ, and a few others get included every year. But all the other ones get included every second year. So it takes, so for example, this is January 2017, this is January 2018, you'll have the 2 issues that cover the last sort of scale of databases that are, and here we have databases on every topic, so from a lot of cancer stuff, of course, but also nucleotides, proteins, protein interactions, 3D structures, and RNA, various types of RNA, and so forth. So I'm just going to spend a couple of slides on talking about GenBank flat file. So that used to be my job. I used to be in charge of GenBank when I was at NCBI. And it's basically, the GenBank flat file, it's funny, I was at a conference many years ago. They asked,